Hello everyone, today we're going to talk about the X-ray imaging system again. Today we're really going to be focusing on different parts of the X-ray circuit. So I'd like you to first look at the diagram on the right-hand side. Let's take a look at this portion of the X-ray circuit. What I want you to notice is that at the far left, where it says line monitor, remember this is where the incoming power from the power company is going to be entering into the hospital and eventually into your X-ray circuit. Remember that the power company is not able to consistently give you exactly 220 volts, so therefore we have this line compensator. It's going to put that number exactly at the 220, and from that 220 then we're going to be able to bring that 220 volts up or down slightly by the use of the auto transformer. On some pieces of equipment, remember, the auto transformer has major taps for increments of 10 kilovolts and minor for increments of 1. As we progress from the left to the right on this diagram, we can see then you've got then the Kvp meter. Remember, the Kvp meter is in the low voltage portion of the circuit because it is on your control console. And then what I want you to notice where the blue arrow is pointing, this is where your timing circuit is located. So the timing circuit is its own circuit, and it's going to be located between the auto transformer and the step-up transformer. Why do we have a timing circuit? A timing circuit is there to terminate the exposure. Remember, when you take the X-ray, you push the button down to start the exposure, but you don't have to lift your finger back up in order to stop the exposure. That's accomplished through the timing circuit. So the radiographer starts the exposure and the timing circuit is there to end it or stop it. The timing circuit is a separate circuit whose role is to make and break the high voltage flowing from the X-ray tube. So remember, it is going to stop the X-ray or tube current, I should say, from flowing from the cathode to the anode. The location of the timing circuit is going to be, as I said, between the auto transformer and the step-up transformer. On most diagrams, it's going to be drawn as a rectangle somewhere between the auto transformer and the step-up transformer. There's 4 types of timing circuits that the book talks about. There is the synchronous timer, the electronic timer, the mass timer, and the automatic exposure timer. We're going to take a look at some important points that you need to know for each of these types of timers. For the synchronous timer, it uses a special type of motor called a synchronous motor. Its minimum exposure time possible is 1/60th of a second. And it cannot be used for serial exposures. Serial exposures mean one right after another. And the reason for this is that you have to manually reset the timer after each exposure. Electronic timers are the most sophisticated type of timer. They're the most accurate, and they're the most complicated. They are accurate to times as low as 1 millisecond. And they can be used for serial exposure, such as in angiography, where we take one image right after the other very quickly. For mass timers monitor the MA and the exposure time. They terminate the exposure when the desired mass level is attained. And mass timers monitor the actual tube current, which is that flow of electrons from the filament to the anode. And therefore, they're located on the secondary side of the step-up transformer. So mass timers are a little bit different They're located on the secondary side of the step-up transformer. And automatic exposure timers terminate the exposure when the IR has received the required radiation intensity, whatever that is based on the anatomic part that you set up that you're X-raying. Let's talk a little bit about automatic exposure controls. If we look to the two diagrams over on the right-hand side, you can see one is your typical photo timer, which is on the left. And then on the right, this would be the type of AEC that we use today. Notice both of them are going to eventually give feedback to the exposure switch to terminate the exposure. So previously, the equipment incorporated a photodiode that when it received a quantity of light from an irradiated fluorescent screen, terminated the exposure. So I want you to look at that drawing for a moment. That's the one on the left. This is photo timing. The X-rays go through the patient. They actually go through the image receptor, and they strike a fluorescent screen. Remember, fluorescent screens light up or give off light when they're struck by radiation. That radiation then strikes the photodiode, which then that information would be fed to the exposure switch. So the important thing is, notice the location. Okay, the location is underneath the image receptor. Today, AEC uses flat parallel plate radiolucent ionization chambers. So these chambers are radiolucent. I want you to look at where they're located. They are actually on top of or above the image receptor. Because they're radiolucent, though, they're very, very thin, they're not going to be imaged on the image receptor. So when the chamber is irradiated, ionization occurs within it and creates a charge. So basically your ionization chambers are air-filled. There is a component that is in there that is going to be able to accept the electrons that were dislodged by the radiation coming off of the irradiated air molecules. And when you reach a certain charge, it's going to terminate the exposure. Now I want you to notice sometimes you still hear the term phototiming. The tech may say, oh, did you phototime that? Okay. What the tech is really meaning to say is, did you use AEC? Because as I mentioned, there really isn't phototiming out there today. It's all generally done through ionization chambers. It's not to say that there might be some old equipment somewhere that still is using a phototimer, but like I said, it's mainly the ionization chamber. So as you irradiate this chamber, electrons are being dislodged from air molecules. They're being collected by a positive element within the chamber. And once a certain charge has been reached or received, then the exposure is terminated. Now, what is that charge or what is that exposure? Well, that's going to be predetermined at the time of installation. So at the time of installation, the technician who is installing the equipment is going to use phantoms, take images, show the radiologist or quality control tech, what do you think about these images? They're going to say, yep, they either look good or they don't look good. If they look good, however, an amount of exposure was necessary to produce that image, that would be the amount of exposure that would be then calibrated into the chamber so that you could terminate the exposure. On some equipment, you do have to manually set up a backup timer. On other pieces of equipment, it's done automatically for you. If you have to manually set up, The general rule is to set it up 1.5 times the anticipated exposure time. Why do we use a backup timer? It's a means of patient protection should the AEC fail to terminate the exposure, that after you hit that backup time that is set up, the exposure would be terminated. Let's move on to the high voltage generator. The high voltage generator is responsible for increasing the output voltage from the auto transformer to the kilovoltage. So notice voltage to kilovoltage necessary for X-ray production. There's a drawing, this is out of Bouchon, showing you the high voltage generator. And in some of your older rooms, you can see this off to the side. It's a box-filled structure, and inside of that, then you're going to have your various transformers, and there is going to be then oil actually that is surrounding them as a means of both cooling and insulation. So the high voltage generator consists of 3 parts: the high voltage transformer, the filament transformer, and then the rectifiers are in there too. You may say, well, what are the rectifiers? We're going to talk about those today. As far as the high voltage transformer, it's the step-up transformer. Remember, a step-up transformer means that there is more turns on the secondary side compared to the primary side. When we say step up or step down, what we're referring to are what are the changes in voltage. So if we have a step-up transformer, we're going to bring up the voltage, but at the same time, the amperage is going to go down, and vice versa then for a step-down transformer. The ratio, remember, of the number of secondary windings to the number of primary windings is termed the turns ratio. We learned that term before, the turns ratio. How many windings are there on the secondary side compared to the number on the primary side, the turns ratio. Very, very, very important. Transformers can only operate on alternating current. Transformers only operate on alternating current. Now, when we look at the circuit, and I have 2 drawings here. The first one at the top is from Bouchon. The second one at the bottom is from Carlton. Now, I don't know exactly what diagram you are going to get on the registry. It will be similar to one of these. Look a little bit different, but what's important, and we'll go through this at the end of this slide presentation, the components are always going to be in the same location. So I want you to look at this. Look at where the incoming power is. That's all the way on these drawings on the left. What's all the way on the right-hand side is your X-ray tube. So if we think about this, the power company is going to give us power in the form of alternating current. However, our X-ray tube only can have electrons flowing from the cathode to the anode, only in that one direction, cathode to anode. Well, that's direct current. Remember, current flowing in one direction is DC. So somehow, between the incoming power and the X-ray tube, we have to change the AC into DC. When we look at the drawing, however, what do we have? We've got transformers. Transformers, remember, only operate on alternating current, AC. So look at where the step-up transformer is. And you can look at the step-up transformer also in Carlton, which would be number 5 on that drawing there. Or the step-down transformer, which would be number 8 in the Carlton drawing. these transformers need alternating current to operate. The tube current, remember, is the flow of electrons from the cathode to the anode, and that has to be only in one direction. So therefore, after the step-up transformer, we have to have some device that is going to turn the AC into DC, and that's the job of the rectifier. Now, what does it mean to rectify something? To rectify something means to change it. And in this case, what we're going to be doing is changing the AC into DC. I point out on the the Bouchon drawing at the top, two rectifiers. Okay, there is a rectifier that I've identified, rectifier for MA meter. Now remember, your MA meter is always found in the middle of the secondary winding of the step-up transformer. In this case, Bouchon has connected that meter to a rectifier. That's with the little arrows and lines, and it's in the shape of a diamond. And also that meter, that MA meter, you'll always know an MA meter by its location, and also it has this little drawing that's there, which is the grounding element. Remember, the MA meter always has to be grounded because it is on the control console, but now it's in the secondary or high voltage portion of the circuit, so it's got to have some type of means of being grounded. So the point being, that little diamond there is not the rectifier for the entire circuit. It's the rectifier for that little meter there. The rectifier for the circuit in Bouchon's drawing are those four arrowheads that are almost in the shape of like a little rectangle there. In the drawing for the circuit in Carleton, the rectifier is drawn in the diamond formation. So once again, the drawings may be a little bit different here on the registry, but the location will always be the same. The rectifier will always be between the step-up transformer and the X-ray tube. The rectifier will always be between the step-up transformer and the X-ray tube. Now you might say, well, how come then the step-down transformer does not have a rectifier after it? And the reason for this is that the filament can heat up, because that's what that transformer is for the heating up of the filament. The filament can heat up just fine with AC. It doesn't need DC to heat up the filament. So therefore, no rectifier is needed in the filament portion of the circuit after the step-down transformer. So as I mentioned, the position in the circuit is critical. Rectifiers are located between the secondary side of the step-up transformer and the X-ray tube. And their purpose is to turn AC into DC, and this is accomplished by what are called diodes. They're drawn on diagrams as these little arrows with the little line after it. And these diodes allow current to flow in only one direction. They're like little one-way street signs that say, okay, current, you can flow in this direction, but you cannot flow in this direction. Before we talk a little bit more about the individual type of rectifier, I want to make sure that you understand what is happening with alternating current as far as a diagram is concerned. In alternating current, or in AC, the electricity, remember, pulses first in one direction and then it reverses and it travels in the opposite direction. So I want you to look at the drawing. I want you to look at the little piece of wire with the electrons flowing through it. And remember, when the pulse is either up or down, the electrons are flowing in one direction, and then when it's the opposite, they're going to flow in the other direction. If we continue reading, for the transformer to operate correctly, this is important. Remember, it allows then, as the electricity is going through the coil, through that primary coil, it's allowing a magnetic field to grow around the coil, and then it's going to collapse as the electricity reaches the other side, and then it's going to turn around. So every time that you get to that middle horizontal line, as far as a diagram is concerned, that's when it would collapse, meaning the magnetic field would collapse, and then it would start to grow again till it reaches a peak, and then it collapses again. So you have this growing and collapsing. Now that's going to be important if we go back to Faraday's experiment. Remember, Faraday's experiment said that if you have movement involved and you're breaking the magnetic field, that you're going to induce electrons to move through the secondary coil. Now, in a transformer, there's no physical movement. If you remember from Faraday's experiment, he actually moved a coil back and forth through a magnetic field. But in a transformer, the movement is provided by the growing and collapsing of the magnetic field itself. Now remember, in the X-ray tube, electrons have to flow only in one direction. And to accomplish this, a rectifier is placed between the transformer and the X-ray tube. And rectification is accomplished through diodes. That's those little arrows with the line that we saw. In a drawing, if we look at this, I want you to notice where it says current and no current. So we have to differentiate between current or electron flow. Remember, we learned current and electron flow are in what? They're in opposite directions. So if we look at this, the electronic symbol for a diode is shown. Current flows in the direction of the arrow, while electron flow then is against the arrow. So it's not written on there, but if current is flowing with the arrow or in the direction of the arrow, that means electron flow would be in which direction? The opposite, so against the arrow. So current flows with the arrow in a diode, but electrons flow against the arrowhead. It's a little bit confusing, but just look at the drawing. Current flowing one direction. What do we know about electron flow? It's in the opposite direction. So current flows with the arrow, electron flow is against the arrow. Originally, the diodes that were used in circuits were called valve tubes, and valve tubes they're very similar to X-ray tubes in that they had a cathode and an anode, and of course electrons can only flow from cathode to anode. Today, however, we use silicon solid-state diodes. Either one of those valve tubes or the silicon solid-state diodes will allow electricity to flow in only one direction. Now, this is a really busy slide, but there's a lot of information here that we're going to take apart, and we're going to go a little bit slow here. I want you to look at the drawing at the top left. This is a drawing showing you a solid-state rectifier. Solid-state rectifiers are actually made up of two types of semiconductors. Now, what is a semiconductor? A semiconductor allows current to flow in some instances, but not in others. When we look at the solid-state semiconductors here, we have an N-type and a P-type. So we usually refer to these types as being called PN junctions, meaning that there's going to be an area where the P semiconductor butts right up against the N semiconductor. The N, if you look at the drawing, has within it loosely bound mobile electrons. They're able to move. And the P type semiconductor has spaces or holes, and those also are able to move. Now, when you look at this, I want you to notice the top drawing. I want you to look at the N semiconductor, and then right next to it, do you see it says negative? And then on the P semiconductor, I want you to look at that side, and there is a positive side. Now, what that represents, if we go over to the right, all the way at the top, here's the sine wave representing electricity as it flows through means of cycles, right? And we've got then a positive side of our cycle and then a negative side. So if we look now to the bottom left of this slide, if a higher potential is placed on the P side, the plus by the P, if you look at the top drawing, the plus by the P, the electrons and the holes will migrate to the junction, and the electrons jump the gap into the holes and allow them to continue to flow through the circuit. So if you've got a higher potential on the P side, look at the P, there's the plus. Well, if you got a plus on that side, the other side of the semiconductor has to be negative. Well, what did we learn about electrons which have a negative charge? And then we're putting a negative charge on to that N-type semiconductor. Like charges do what? They repel. So even though holes aren't positively charged, we can kind of think of them like that, in that if you got a positive charge coming in on that side, it's going to repel those holes toward the middle. If you got a negative charge coming in on the N semiconductor, it's going to repel those electrons away, and it's going to push the holes and the electrons together, allowing the electrons to jump into the holes and continue on their way. Notice there's an arrow, a dark arrow that says electron flow across the junction. Now, what do we know about alternating current? With alternating current, then, after the electricity flows in one direction, then it flows in the opposite direction. So now I want you to look at the drawing at the bottom, same PN junction we were looking at. I want you to notice now the change in the signs, positive and negative. Look at the N-type semiconductor. Well, now instead of negative at the top, it's positive. Do you see the change? And then look at the P junction, or P semiconductor. At the top, there was a plus. You see the P and then the plus. Well, now it's a P and a minus, negative. So our alternating current has shifted now, and now the N semiconductor is positive, or has a positive charge on it. The P has a negative. Well, what do electrons do? And these are the electrons that are in the N-type semiconductor. If you put a positive charge coming in, opposites do what? They attract. So the positive is going to attract the electrons. The negative, now remember I said holes aren't exactly positive charges, but think of them kind of like that, in that they're pulled toward the negative. And now notice that you do not have any electrons that are going to jump across from the N to the P. So notice what it says at the bottom. No electron flow. Let's take a look at the drawing down at the bottom on the right. Okay, I want to kind of help you to understand this by means of a diagram. Okay, if we look, and let's start with electrons flowing where it says AC supply. I want you to imagine that the electrons are going to flow from the A and eventually get to the other side of the circuit, the B. So as the electrons start to flow, they flow through the resistor. And remember, what did we learn about a diode? Electrons can flow against the arrow. So the electrons continue on their way until they get to position B. That basically then would put the first half of the cycle on a drawing. So look at the bottom where the two cycles are drawn. Look at the bottom drawn, and you've got your first hump. That would be going from A to B. Now what happens with alternating current? Then it switches, right? So now the electricity is going to flow from, or it's going to want to flow from B to A. So it starts out, the electrons start flowing from B. Look at the red arrows. They get to the diode, but what did we learn? Electrons cannot flow with the arrow. They only can flow against it. So at that point in time, the electricity actually is stopped. Take a look at the bottom drawing there. Notice the half of that cycle, the hump that would be below the horizontal line, it's gone now. And then what does electricity want to do then? AC? Well, now we're going to flow again from A through the resistor. The electrons can flow against the arrowhead to B, so we get another hump. There's the second hump on that bottom drawing. And then we start to flow from B going to A, but electrons cannot flow with the arrow, so they're stopped. That bottom part, that bottom hump now underneath the horizontal line is gone again. So what we're doing when we have this configuration is we are creating something called half-wave rectification. Basically, what have we done? We've allowed half of the wave to go, and the other half is gone. Take a look at the top drawing, the unrectified AC. So I've drawn in black arrows there. So on the top hump, the electricity would be flowing in one direction. Remember the bottom half of the cycle, the bottom hump, it would be flowing in the opposite. If we get rid of the ones on the bottom, which would be the second drawing there, got rid of the ones on the bottom, what are we noticing? We're noticing the electricity now only doing what? Only flowing, or being able to flow, in one direction. So this would be good if we had this, because it would allow then our electrons to flow from the cathode to the anode only. But what have we done? We're wasting half of the electricity. We've actually kind of canceled out half of our electricity. So half-wave rectification is not the most efficient, but it works. It allows electrons to flow through the tube from the cathode to the anode. If we look at the top drawing, this is out of Carleton, in low-powered units, the tube itself may act as the rectifier. I want you to look at this drawing in Carleton and notice after the step-up transformer, but before the tube, there's no rectifier that's really drawn in there. If it's low power, what can happen? Well, electrons can flow from cathode to anode, and then what happens? The electricity reverses, but can electrons flow from the anode to the cathode? The answer is no. So at that point in time, the tube would be acting as the rectifier. So in low-powered units, the tube itself could act as the rectifier. This is termed self-rectification. So if you have the tube acting as a rectifier, electrons flow from cathode to anode. That gives you the top pump. Then the electricity switch is going the other way, but electrons cannot flow from the anode to the cathode. The bottom hump is gone. So you're getting half-wave rectification. In order to make it more efficient so that you're not getting rid of half of the energy, if you incorporate into your circuit, and this is key, 4 diodes, and I want you to look at the drawing over to the right. This is out of Bouchon. I've numbered these for you. 1, 2, 3, and 4. Now what this drawing is showing you, that the top drawing and the bottom in combination, what did I say diodes are like? Diodes are actually like one-way street signs. And they say, okay, electricity, you can flow through me and go in this direction, but you can't flow through me and this diode. I'm not going to let you. So they're acting as one-way street signs, kind of to allow electrons only to flow through the tube from the cathode to the anode. In order to accomplish this, you need to have 4 diodes wired correctly into the circuit. If we take a look at the drawing over on the bottom left, okay, here we've got at the top and just a typical AC current with the up hump there representing the positive side of the cycle and the bottom, the negative side. What you do when you incorporate 4 diodes into the circuit and you put those one-way street signs in there, so to speak, allowing electrons to only flow from the cathode to the anode, you actually take the bottom humps, those parts of the circuit below the horizontal line, and I drew red arrows showing you flip them up. So basically, what's happening, we're only allowing then electricity to flow in one direction. This is termed full wave rectification. So with full wave rectification, there is no loss of the electricity like you had in half wave. Now, if you want to study the actual path of the electricity flowing through the tube itself, Carlton has a very good description going through each of the diodes as the electricity flows through it. It's not anything you have to memorize for the registry, but you need to know that rectifiers are there to change AC to DC. If you want to have full wave rectification, which means that you're going to utilize all parts of the AC cycle, you're going to need at least 4 diodes incorporated into your circuit. Now, in the United States, we generate power at 60 cycles per second. Well, we have to remember, what is a cycle? 2 alterations in a wave. So with 60 cycles per second, we've got 120 alterations in the wave per second, right? Because 60 times 2, 60 times 2, 120. With non-rectified, we get that 120 pulses per second. If we half-wave rectified, what did we do? We got rid of half of each of the cycles. So now we only have 60 pulses per second. And with full wave, what did we do? We didn't get rid of them. We actually flipped the ones that were on the bottom up to the top. We're back to the 120 again, 120 pulses per second. So non-rectified, 120 pulses per second. Half wave rectification, you got rid of half of them, so you only have 60 pulses per second. And with full wave, you use both parts of the cycle. You flip them, allowing electrons only flow in one direction, so we've got the 120 pulses per second. With half-wave rectification, because half of the cycle is wasted, techniques would require twice or 2 times the exposure time to achieve a proper IR exposure. And with full wave rectification, because we're using both parts of the cycle, we're using all the electricity, you can actually cut your techniques in half. When we look at the diagrams of waveforms, I want you to look, we've got a horizontal line going across, and then we've got these waves of energy in a sinusoidal pattern, up and down. And I want you to notice the top statement. When the voltage wave drops near zero, the horizontal line, the X-rays generated are a very low energy. So at the horizontal line, that's zero. The horizontal line is zero. And then as look at number 1, as it starts to go up, the green, it reaches a peak value. That's the highest voltage X-rays that would be in your technique. That represents the highest voltage techniques. And then what starts to happen is you start to go down again, back down towards zero. So we've learned this when we learned KVP, that when you set up a kilovoltage peak, that the peak value means that that's the highest keV X-ray photons that can be in that technique, but there's actually very few of them. Well, now you can see diagrammatically why that is. Your KVP, your top peak values, are only at the tops of the waveform or at the crest. Through sophisticated electrical engineering, 3 electrical waveforms can be generated and placed slightly out of phase with one another. So if we look at this, we have the green being number 1. That represents one phase of electricity going through the circuit. Then we have another phase slightly out of sync, number 2, and another phase slightly out of sync, number 3. If we can rectify that, then we can even take those ones on the bottom and flip them up to the top, allowing the electrons to be flowing in only one direction. But I want you to look at this bottom drawing. If we look at this, what happens, and what did I tell you? We start out at 0, the horizontal line, we work up to a peak value, and those are your most energetic photons. When you use 3-phase rectification, the next phase, in that instance number 2, imagine you're going up the green, and then you start to go down, and then you hit number 2 and it picks you right back up to the top. And then you start going down with number 2, and then you got number 3 that picks you right back up to the top. It doesn't allow the voltage to decrease that much. And this is what the bottom drawing is trying to show you. Look at, you're starting in red at the horizontal line. You work up to a peak value, peak voltage. It starts to drop down. The next one comes along, picks it right back up, the blue. It starts to drop down. The next one comes, picks it back up, blue. So look at the blue. You're staying up near the top of the voltage waveform. So as one phase starts to drop, another wave comes along to keep the voltage always near the top, yielding higher energy X-rays. That's shown to you in blue there. If you rectify it, as I said, the higher energy electricity will travel in only one direction, resulting in 3-phase direct current. Today, most equipment is what we call high frequency. Special circuitry is used. It's called inverter circuits. They show this a picture of this to you in Bushang. Inverter circuits use high-speed switches, something called choppers. They're used, and the electrical voltage is nearly constant, allowing for improved image quality and lower patient dose. So what is desirable is to keep the waveform up near the top of the crest. Don't allow it to drop back down to your horizontal line. If we can keep it up near the crest, we're utilizing the highest voltage X-rays for our technique. And this is where we get to something called voltage ripple. Okay, just think about ripple like waves. If I had a pond, a still pond, and I took a stone and I threw it into the middle of the pond, I'd get these little waves, these little ripples. Okay? Kind of like what we're looking at here when we look at the waveforms for the electricity. So it says another way to characterize voltage waveforms is through a concept termed voltage ripple. The less the amount of voltage ripple, the more efficient is the imaging system. This is important. The less the amount of voltage ripple, the more efficient or better is the imaging system, because the voltage is remaining near the top of the crest of the waves like I showed you on the previous slide. Less voltage ripple results in greater radiation quantity and quality. So this is what you desire. You desire less ripple. Continuing low voltage ripple increases radiation quality. Why? Because fewer low energy projectile electrons pass from the cathode to the anode to produce those low energy X-rays. Therefore, the average X-ray energy is greater than that resulting from high voltage ripple modes. So if we take a look at the drawing, half wave is said to have 100% ripple, because remember, we start out at the horizontal line, which is 0. We work up to a peak value, and then what do? We drop all the way back down to 0. And then in half wave, we've got a gap, and then we start another cycle, 0 peak value, back down to 0, and then a gap. So the ripple is 100%, 0 to the top of the peak, back down to 0. Full wave, although it's better because you're utilizing that part of the cycle that was below the horizontal line, we've flipped it up now, it still has 100% voltage ripple, because you're still starting at the horizontal, working to a peak value, dropping back to 0, working to a peak value, dropping back to 0. So still 100% ripple. Now, if we use three-phase, where we have those phases of electricity slightly out of sync, where as one starts to drop, another phase comes, picks it right back up, it starts to drop, another phase comes, picks it right back up, we get much less voltage ripple, which means that our X-ray techniques, they're more efficient. We can use less radiation. Three-phase 6-pulse gives you 14% ripple. If we, or an electrician, rewires the circuit a little bit to allow three-phase 12-pulse, well, now you only got 4% ripple. And today, with most of our generators being high frequency, we get less than 1% voltage ripple, which is very, very desirable, because we're keeping, it's almost, what would be the most desirable is to have a straight line across the top. Well, we can't get that because electricity travels in the form of waves, but we're getting very, very close to that straight line with high frequency. So the last statement on this slide, three-phase equipment may require as much as a 10 kVp decrease to produce the same IR exposure when operated at the same mass as single phase. And with a high frequency generator, you could decrease your kilovoltage by 12. Why? Once again, as you're going from single phase to three phase, the equipment with three phase is much more efficient. It's giving you a higher quality beam, higher quantity of photons. Power rating. A high voltage generator for a basic radiographic unit is rated at 30 to 50 kilowatts. Interventional radiographic equipment, like you'd use in a cardiac cath or interventional suite, 150 kilowatts, so much more power is needed. And lastly then, we've got our whole circuit. Okay, let's do a quick review of the circuit before we end. So on this drawing out of Bouchon, we've got what would be on the control console, the high voltage section, and then the X-ray tube. So in this case, our power is flowing in from the left. We're going to have the line compensator to bring it exactly to the 220 volts. Notice the Kvp meter. Notice the timing circuit. Notice the step-up transformer. On the secondary side of the step-up transformer, connected right in the middle, is our MA meter that's grounded. Then we have our rectifier. That's the 4 diodes there. And then we have our tube. As far as the bottom portion of our circuit, this is the filament portion. Remember that our MA selector is there, which is a variable adjustable rheostat that's going to allow for us to get more or less milliamperage. Remember, to heat up the filament requires low voltage but high amperage. So we have a step-down transformer. And to heat up the filament, you can heat it up very nicely with AC. We don't have to turn it into DC, so there's no rectifier between the step-down transformer and the X-ray tube. So there is your circuit. I want you to look at this drawing. You need to memorize it. You need to memorize the components of the circuit in order. And then I want you also to look at Carlton, look at that drawing. And once again, you're going to see it's drawn a little bit differently, but everything is in the same order.